For decades, making a computer program run, just a tiny fraction of a second faster cost companies millions of dollars.
Oh yeah, millions.
Yeah, millions in highly specialized engineering time. But today, an AI agent can basically do it for pennies while you sleep.
Right, and we are looking at a complete inversion of how the tech industry values software optimization. I mean, it fundamentally changes what software is actually capable of doing.
Exactly. So welcome to our deep dive. Our mission today is to explore this massive paradigm shift in computer science. We are breaking down a really comprehensive technical essay by Dan Liu, and it's titled, "There's No Reason for Software to Be Slow Anymore."
It's a bold title, for sure.
Right. And we're pulling from his detailed experiments on things like regex engines, game AIs, and search indexes to understand how AI coding agents are driving the costs of elite, highly specialized performance optimization down to nearly zero.
Yeah, and the premise of this essay challenges a very common assumption about the future of AI-generated code. It really pushes back against this idea that, automation will simply lead to bloated or inefficient systems.
Yeah, so before we get into the heavy technical details of those experiments,
Yeah.
I want you to think about buying a mass market car. You accept that it's built for the average driver. It's a compromise. It's tuned for highway driving, city traffic, maybe a little snow.
Right, because the manufacturer engineers that vehicle to be just, good enough for millions of people. Customizing the mechanical baseline for every single buyer would cause production costs to completely skyrocket.
Yeah, totally. But imagine if while that car was parked in your garage overnight, an invisible team of engineers took it apart and redesigned the shape of the engine's gears specifically to match the exact steepness of your personal driveway.
Wow.
Right? Or they'd tune the suspension specifically for the exact distance between the potholes on your specific street.
Yeah, applying that level of hyper-customization to the physical hardware sounds absurd, right? But we are standing on the edge of exactly that reality for the digital tools and software platforms that we interact with every single day.
Okay, so let's unpack this, starting with what's basically a prevailing myth right now. There's this viral sentiment floating around the tech community that AI is just going to lead to incredibly slow, bloated software.
Right, I hear that all the time.
Yeah, the logic goes that because AI can generate code so quickly, developers will just pump out mountains of sloppy, unoptimized junk without taking the time to actually refine it.
Right, but the source text counters that directly by pointing to this concept from developer Nolan Lawson. So Lawson observed that with the advent of AI assistance, you can choose how many bugs you want now.
Okay, wait, what does that mean?
Well, Dan Liu argues this same principle is becoming true for performance too. Basically, the ceiling on efficiency is lifting, meaning you can simply choose your performance level based on how much compute time you want to dedicate to optimizing it. You just let the AI run longer. Ah, I see. And to understand why that represents such a radical shift, we really have to look at the historical baseline. Because the reason software has traditionally been slow isn't because developers are bad at their jobs.
No, not at all.
It's an economic bottleneck, right?
Wow.
Like, truly optimizing code to run as fast as the silicon allows requires a rare, highly paid team of specialists.
Extremely highly paid.
Right. So if a business has to choose between spending $1 million on a performance team to make a button click, I don't know, 10 milliseconds faster,
Right.
or spending that same money building a brand new feature that customers will actually pay for, they choose the feature every time.
Every single time. Performance optimization was simply too expensive to justify for all but the largest scale or most lucrative projects out there.
Yeah.
But the source notes that the cost of this formerly specialized performance work has dropped by orders of magnitude. And I mean a staggering drop, like 1,000x to 1,000,000x in cost reduction.
That is just wild. Yeah. A piece of performance work that used to require an entire team with this rare set of architectural skills can now be initiated by typing, a few sentences into a prompt.
It's like having that team of Formula One mechanics suddenly available for the price of a standard oil change.
Right, exactly.
Instead of just tuning the engine, they are entirely redesigning the fuel injection system for your specific commute. Like, you wouldn't normally tune a family minivan for the racetrack because the labor would cost an absolute fortune. But if the tuning labor is essentially free, there's literally no economic reason not to do it.
Right, right. And the essay highlights this insight from Michael Malice, who pointed out a common meme in tech, which is that code was never the hard part of software engineering.
Oh yeah, you hear that a lot.
You do. The traditional thinking is that system design, architecture, or, just understanding user needs was the real challenge. But Malice pushes back heavily on this. He says in some domains, writing the actual code was absolutely the hard part. And he points specifically to JIT compilers, just-in-time compilers and databases.
Yeah, and JIT compilers are notoriously complex. Just for a quick baseline for the listeners, instead of translating a program into machine code all at once before it runs, a JIT compiler translates the code on the fly.
Right, while it's running.
Exactly, while the program is actively running, dynamically analyzing the execution to make it run faster as it goes.
Which is incredibly hard to write, and Malice brings this complexity up in the context of a project called Prust.
Oh,
So Prust is this initiative to allow developers to write custom extensions for PostgreSQL databases using the Rust programming language.
gotcha.
Now, Rust is incredibly fast and it's memory safe, but bridging it with the complex legacy internal architecture of a massive database like Postgres.
That sounds awful.
It is. It's traditionally a coding nightmare. The sheer amount of boilerplate and intricate mapping required would just deter most teams from even trying. But because LLMs have lowered the barrier to writing these intricate, hyper-specific bridging structures, developers can suddenly be vastly more ambitious. The sheer difficulty of writing the code itself is no longer the impenetrable wall it used to be.
Which means the excuse of, it's too expensive to optimize, that excuse is dead.
It's completely dead.
So I want to look at what happens when a complete novice actually wields these new tools against established human experts. Because the author of our source text actually tested this boundary.
Yeah, this part was fascinating.
Yeah, with zero prior knowledge of game AI architecture, he used an LLM to build an artificial intelligence for the board game Azul.
And he ended up building the strongest Azul AI in the world.
Wait, literally in the world.
In the world. Beating systems built by people who dedicate their entire careers to this specific niche of game theory and programming?
That is insane.
Yeah, and he suspects his system wasn't necessarily smarter in its core logic or its heuristics. It basically won on pure brute force optimization. Specifically, the AI implemented multithreading, while the previous second-best AI in the world was entirely single-threaded.
Okay, so multithreading is a concept we hear a lot, but to break down the actual mechanics of it, it's about breaking a computational task down so multiple processor cores can work on different parts of the problem simultaneously.
Exactly.
Like a single-threaded program has to wait in a single file line to process data. Multi-threading basically opens up multiple checkout lanes at the grocery store.
Right, but implementing that is much harder than it sounds. Like
Yeah.
building two completely different search architectures that require different multi-threading algorithms by hand, that is a massive undertaking for a human.
Oh, for sure.
A human developer has to deal with concurrency, memory sharing, and the dreaded lock contention.
Wait, break down lock contention real quick.
Sure, so lock contention happens when two separate threads try to access or change the exact same piece of data at the exact same millisecond.
Oh, okay, like two cashiers trying to scan the same barcode.
Exactly. And that can freeze the entire system in a deadlock, or worse, it can corrupt the data entirely. But the author bypassed all of this manual architectural planning. He just let the AI pick the algorithm.
Wow.
Yeah, and when the AI got it wrong, he spent maybe 30 minutes reading up on the underlying concept, and then just had the AI rewrite the complex code multiple times until it functioned properly.
Yeah, and the text highlights the sheer tediousness of debugging non-deterministic multi-threaded code.
Yep.
Because, threads operate independently, so you get these ghost bugs that only happen maybe 1 out of 1,000 times based on the exact microsecond timing of how those threads interact.
They're a nightmare to find.
Right. Using replay logs to track down a bug that refuses to happen consistently.
Right.
That takes the human developer days or weeks of grueling hair-pulling work. But an AI agent does it trivially in just a continuous loop. It runs the code, fails, inserts deep logging statements to track the exact state of the memory, tries again, endlessly. And it does it without ever losing focus or getting frustrated.
Which is key, because the performance gains from surviving that tedious loop are undeniable. The text notes that in this specific game environment, a player gains about 100 ELO, which is the standard rating system of player strength,
Right.
for every doubling in processing speed. So just adding that multi-threading capability wiped the floor with comparable AIs. Stacking 10 to 20 of these incredibly tedious optimizations on top of each other creates a tremendous difference in computational strength.
Yeah, a handwritten AI simply cannot keep up with that volume of iterative testing. It's just impossible.
Yeah, the AI is outworking the human by a factor of thousands. And there's another wild example in the text about a performance engineer named Jamie Brandon.
Oh, the Anthropic test, right?
Yes. So he took Anthropic's public performance take-home test. And this is a gauntlet designed to challenge top-tier engineers applying for jobs at one of the leading AI companies in the world.
Right. These are the best of the best.
Exactly. And he did well enough to get the job offer, but then he ran an experiment. He had the AI model, Claude, pick up exactly where he left off in his own code base.
And what happened?
The AI absolutely crushed his score.
Wow.
Yeah. Jamie noted that some of the optimizations were things he had actually thought of, but just hadn't had the time to implement due to the time constraints of the test.
Sure, that makes sense.
But others were, in his own words, crazy shit that he would never try unless he was working on this for weeks. As a highly skilled professional working on a well-defined optimization problem, even he admits he doesn't stand a chance against a decent model given comparable time constraints.
Okay, but here's where it gets really interesting, though. Because I have to push back on this premise based on a specific detail in the text.
Okay, what's that?
The source explicitly mentions that current state-of-the-art models are actually terrible at experimental design. So how is an AI beating a human expert like Jamie Brandon if the model doesn't even know how to properly design the experiment to test its own code?
That is a great point. And the text delineates a crucial difference between an open-ended problem and a bounded optimization problem.
Okay.
If you offer no structure and simply tell an AI, hey, make my software better, it fails. It completely lacks the human judgment to set up a rigorous testing environment. The human still has to be the architect. They have to lay the track, set the rules, and define what faster actually means by setting up the benchmarks.
Right, so you have to give it a playground with strict walls.
Exactly. Once that framework is in place and the problem is strictly bounded by human parameters, the AI can run 1 million optimization laps faster and cheaper than any human alive.
Okay, so the human builds the laboratory, but the AI is the tireless lab assistant running 10,000 chemical reactions overnight.
That is a perfect way to put it, but there is a massive trap here. Because if you give an AI a rigidly bounded test to optimize for, it won't necessarily learn to write fundamentally better code. It will just learn how to cheat that specific test.
Ah.
The author experienced this firsthand when building a regex engine called FRE.
Okay, so for anyone unfamiliar, a regex, or regular expression engine, is essentially a superpowered text search tool.
Right.
Like, programmers use it to find incredibly complex, specific patterns of characters within massive amounts of data.
Right.
A normal search finds the word cat. A regex search can find, any 3-letter word starting with C, ending in T, but only if it appears at the end of a sentence.
Perfect example. So the author left an AI agent in a loop for a month to improve this regex engine's performance.
A whole month.
A whole month, giving it access to evaluate its progress against a standard benchmark suite called rebar. But because the problem was bounded entirely by that specific benchmark, the AI heavily overfit to rebar.
Right, so without a holdout benchmark, it's like a student who gets their hands on a specific practice test.
Exactly. Like, instead of actually learning the underlying mechanics of the subject, say chemistry, they just memorize the exact answers to that one practice test. They look like a total genius on that test, but if you ask them a real chemistry question they haven't seen before, they fail completely.
Yep.
So the holdout benchmark is basically the surprise final exam. It forces the AI to actually get smarter at searching text in general, not just trick the specific test it was originally given.
That is exactly it. And once the author introduced this holdout benchmark, the agent was finally forced to generalize its optimizations. And the text details a truly wild optimization the AI pulled off here, involving a native AOT or ahead-of-time compiler.
Yeah, this part of the experiment is just staggering. So they have the standard search tool running, but they want it faster. The author spent just a few minutes typing a prompt, right? And the agent wrote code that does something incredibly complex behind the scenes.
What does it do? When a search starts, it runs the standard search engine, but in the background, in a completely separate thread, it starts compiling a custom native machine code version of the search purely for that specific query.
Oh, wow.
And when the custom engine is finished building, it hot swaps it in and takes over the search mid-execution.
Which is insane because the mechanics of how software hot swaps execution paths without crashing are intensely complex.
Right, like changing the tracks while the train is already running over them.
Exactly like that.
Yeah.
You have a program actively running down one track, and you need to switch it to a new, faster track without losing its place in the data or corrupting the memory.
How does that even work safely?
Typically, this involves carefully orchestrated atomic pointer swaps. The system memory address that dictates the execution path is updated in a single, uninterruptible operation at a highly specific, safe synchronization point.
Oh, wow.
Doing this safely is major code surgery. It would take a human developer a significant amount of time to plan, write, and rigorously test to avoid race conditions.
And the agent did it in minutes.
Minutes.
The results were a 2x to 4x speedup on long queries, and even a 7% speedup on those surprise holdout queries, all for just a few minutes of human typing.
Yeah, but we just established that overfitting to a specific test is a massive problem if you are trying to build general software for everyone, right? The software becomes fragile outside of its test environment. But what if overfitting is exactly what you want?
Right. What if you want software that is fundamentally overfit to you?
Yes. And the essay shifts here from how developers build software to how we might personally experience software in the future. The author brings in a concept from Mark Brooker, who is a vice president at Amazon.
Okay.
Brooker suggests the inevitable outcome here is dynamic, custom software fitted to a particular workload rather than a general class of workloads. Brooker compares this to old Damascene techniques.
Right. The Damascene being that subculture of programmers who try to squeeze just mind-bending graphics and audio out of extremely limited older hardware.
Right, doing impossible things with old computers.
Yeah. And to achieve that, they used highly specific, kind of counterintuitive tricks. Like, one technique was reusing the program's executable code itself as visual textures.
Which sounds crazy.
It is, because normally a computer stores image textures in video RAM and the logic code in standard RAM. And transferring data between them takes processing time.
Right, it's a bottleneck.
Exactly. But by mathematically forcing the raw machine code to double as the visual data, they kept everything in the fastest, most immediate part of the computer's memory, bypassing that standard transfer bottleneck entirely.
Wow.
And another example is tools like FFTW, which calculates fast Fourier transforms by actually generating custom C code optimized for the exact hardware architecture it's currently running on. It's hyperspecialization, totally discarding all generalization for pure speed on one exact machine.
And that is exactly what the author decides to test, this hyperspecialization, on his own personal computer. He looks at his own history of search queries, his Codex logs.
Okay, so Codex is the OpenAI model that powers tools like GitHub Copilot, right?
Right. And the author was analyzing his own API request history to see exactly how he uses the ripgrep search tool day to day.
And the statistics he found regarding his own habits are highly unusual. Like 99% of his searches were complex regex patterns. But more importantly, 99.9% of his queries were standard ASCII text, meaning basic English characters. But he was running them against files where 55% of the content was complex Unicode.
Right.
Wait, why does that specific mix of ASCII and Unicode create a bottleneck for performance?
So it creates a massive mechanical bottleneck because of how computer memory reads text. ASCII characters are simple, right? They almost always take up exactly 1 byte of memory.
Okay.
But Unicode characters, which include things like emojis, complex symbols, non-Latin alphabets, their variable length, they can take up to 4 bytes.
Oh, I see.
So when a general-purpose search engine scans a document, it has to constantly pause and check the byte boundaries to figure out if it's looking at a single ASCII character or, the middle of a complex Unicode character.
It has to ask, is this an A or half of a laughing emoji?
Exactly. And if you know you are only ever searching for ASCII patterns, checking all those Unicode boundaries is wasted computational effort.
Yeah.
But off-the-shelf software has to do it just in case, sacrificing speed for safety.
Wow, okay. And his query lengths were also wild. The medium length, the P50, was 55 characters long. His P90, meaning the top 10% of his longest queries, were 119 characters long.
That's a huge search query.
It is. Some of his searches were so mathematically complex they were taking over a minute to run. Off-the-shelf software just isn't built for a user who types 119 character search strings.
No, definitely not. So he takes this bizarre, highly personal data set of his own behavior, feeds it to the agent, and asks it to optimize the search tool specifically for his unusual habits. He basically instructs it to bypass all those generalized safety checks, like the constant Unicode boundary scanning.
And what happens?
In 2 minutes, the agent created a bespoke workload-optimized version of the tool that yielded a 2% speed win on his holdout queries.
2% might not sound like a lot, but it took 2 minutes of human effort for a tool he uses constantly. That adds up.
It adds up fast. And the author notes that if you really wanted to speed things up, the traditional way wouldn't be optimizing the search engine at all. It would be building a full text index of his entire machine.
Oh, wow.
He mentions he used to work on Bitfunnel, which is the Bing search engine index that won a Best Paper award.
Good.
A project like that, which involved constant fast text ingestion and multiple JIT compilers, used to be a massive undertaking for a whole team of top-tier engineers.
Yeah, that sounds huge.
Today, building a blazing fast, custom, whole machine text index with multiple JITs is casually described as a weekend project for a single person using AI.
That is just, it's hard to wrap your head around. So what does this all mean?
Yeah.
Let's bring this down to earth for the listener. If I am a video editor dealing with massive 8K files or, I don't know, a financial analyst crunching sprawling interconnected spreadsheets, does this mean my standard off-the-shelf software is eventually going to mutate and recompile itself specifically for the exact files I touch every morning?
I mean, the data points firmly in that direction. Looking at enterprise applications, imagine a company piloting a program where they analyze a specific customer's data, the exact way their accounting department runs reports, the specific structure of their legacy databases.
Right.
The system then automatically spins up hyper-optimized bespoke versions of the software just for their daily workflow. The software adapts perfectly to the company's unique friction points.
That would change everything.
It would. Because the cost of optimization has plummeted to effectively zero, there is no economic reason not to do this. We are transitioning from a world of one-size-fits-all software to a world of one-size-fits-one.
That is wild. To recap the massive shift we've explored today, the historical excuse that performance optimization is just too expensive, it's dead. We've seen how AI agents can beat human experts on bounded performance tasks simply by out-iterating them, executing massive structural changes like ahead-of-time compiler hot swapping that human engineers wouldn't have the time to risk. Most importantly, all of this points toward a future of hyper-customized, workload-specific software generated on the fly, fitted perfectly to your personal habits.
Right. The traditional barrier to entry for building complex, hyper-fast systems has been completely eradicated. It's shifting the burden from human labor to raw compute.
Which leads to a pretty wild thought. If we truly reach a point where AI agents can constantly rewrite and optimize our local software for our specific daily habits, taking only minutes to do what used to take teams of engineers months, will the new bottleneck in computer science stop being human intelligence and instead simply become the electricity bill for running these AI optimization loops 247 in the background of our lives?
It's a real possibility.
Like while you sleep, the invisible mechanics are working, pulling the digital car apart, putting it back together faster. The only question is, can we afford the power to keep the lights on in the garage?